In this video we will talk about the decay of this reaction NOBr to NO and Br2, but they tell us the decay is second order and the rate constant is 0.80 molar times 0.80 divided by molar times seconds. So second order automatically should clue you in on utilizing these sets of equations for second order. This is the decay profile over time, and this is the equation that will tell us how much it decays and how much is left over, and this is the equation for the half-life. So this is what we need to pinpoint ourselves on with regards to second order decay of a specific reactant. Let's go ahead and read the problem some more. So the rate constant lowercase k is 0.80 divided by molar times seconds at 10 degrees C. Remember, a rate constant is quoted at a specific temperature. Starting initially with 0.086 molar, calculate the concentration of this NOBr after 22 seconds. So this seems to be pretty clear and straightforward of what we need to do. They give us the rate constant lowercase k at a specific temperature, 10 degrees C. Initially we're at 0.086 molar. At 22 seconds, how much of this NOBr, the initial reactant is NOBr, how much of this is left over or decays such that you have a leftover after 22 seconds. So we're going to plug all our important numbers here. Initially the problem tells us that NOBr was at 0.086 m. Okay, the rate constant they tell us, I'm just getting it from the problem here, is 0.80 divided by m times seconds times t. T here is at 22 seconds. Okay, so this is the equation for second order decay now. And all of that must equal to 1 over A. I'll just call it 1 over NOBr because that's for this specific reaction what we're looking at here. So let's do this first. 0.80 times 22, the seconds and seconds cancel each other out. 0.80 times 22 is that number, plus, I'll put my parentheses here, 1 divided by 0.086 plus 1 divided by 0.086. Don't forget those close parentheses. So that's going to equal to 29.23, but that's 1 over NOBr, and that's going to equal to 29.23. If you're wondering about the units here, the units are actually going to be over m. Okay, we can flip this. If we flip this, NOBr is going to equal to, we flip that, so the m comes back to our normal conventional, what we would expect it to be for concentration moles over liter. So flipping this, we have to flip the 29.23. So 1 over 29.23. On my calculator I have a flip it button or inverse button. So getting about 0.034, and let's put our proper units in of big M molar. 0.034 molar. So that's the answer we're getting, and the units also come out proper. Part B of this problem has to do with the half-lives. Calculate the half-lives, which is the time required for 50% of it to decay. When your initial reactant is 0.072, and they ask us to do it again when the initial reactant is 0.054. So again, let's look at our little cheat sheet here. The half-life for a second order reaction. Okay, second order. The half-life, these are the units, but the equation, the units for rate constant lowercase k. Half-life is 1 over rate constant k times the initial concentration. Well, they gave us the initial concentration for this one, and then we've got to solve it for the other one as well. So our half-life for second order decay is this equation. The problem tells us that k is 0.80 divided by molar times seconds. Okay, that's our K. NOBr, our initially is going to be 0.072 molar. Half-life should be in units of some time, so the molar cancels this second in this denominator from a fraction within the denominator, flips up. So 0.80 times 0.072, and then we have to take the inverse of that. And doing that on my calculator, I'm getting an answer of about 17.4 seconds. Okay, so what does this mean? It means that when you're initially at 0.072 molar, for this NOBr to go down to half of that, so what's half of 0.072? We start off with 0.054 molar. Okay, so same principle here. 1 over k, they give us that to us as 0.80 divided by m times seconds. The initial concentration, they tell us in the problem, is 0.054. It's right here. The m and m's cancel, so 0.80 times 0.054, we take the inverse of that. On my calculator, I'm getting an answer of about 23.1 seconds. So what does this mean? It means that if you're starting from 0.054 molar, okay, after 23.1 seconds, or roughly, this thing will decay, and it will decay to whatever 0.054 divided by 2 is. 0.1 seconds, the concentration will go to 0.027, exactly half of this, the very definition of a half-life.